So, good morning, ladies and gentlemen. We will have a distinguished talk, which will be given by Dr. Gabriele Manganaro from Analog Devices from United States of America. One moment, please. I have an echo here. So, the title of this talk is Mixed Signal Technology for Ultra-Wideband Signal Processing Systems. This event has been organized by the IEEE Solid-State Circuit Society of South Brazil chapter. Before we start the talk, I would like to introduce Dr. Gabriele Manganaro. He holds a DR engineer and a PhD degree in electronics from the University of Catania, Italy. Starting in 1994, he did research with ST Microelectronics and Texas A&M University in USA. He worked in data converters, IC design at Texas Instruments, engine incorporation, and as design director at National Semiconductor. Since 2010, he has been with Analog Devices, first as an engineering director of high-speed data converters, and more recently as a technology director for Communication Products Division. He served in the technical subcommittee for data converters of ISSCC for 7 consecutive years. He was associate editor for IEEE Transaction Circuit and Systems, Part 2, and then associate editor, deputy editor-in-chief, and final editor-in-chief of IEEE Transaction Circuit and Systems, Part 1. He authored and co-authored more than 60 peer-reviewed papers, 3 books, notable on Advanced Data Converters, Cambridge University Press, 2011, and has been granted 17 US patents with more pending. He was recipient of scientific awards, including the 1995 CEO Award from Rutherford Applicon Laboratory, UK, the 1999 IEEE Secrets and Systems on Outstanding Young Author Award, and the 2007 IEEE European Solid-State Circuit Conference Best Paper Award. He is an IEEE Fellow since 2016, a Fellow at the IET since 2009, member of the Scientific Honors Society Sigma XI, and was a member of the Board of Governance for the IEEE Circuits and Systems Society in the years 2016 to 2018. Gabriele has received international technical and leadership recognition. He is often invited to speak on technical subjects at key conferences at top universities, and developed a top graduate professional courses in data conversion, design, and mixed signal design at the University of Oxford, UK. So please, Dr. Gabriele, now I will give you the word.
Thank you very much for your kind invitation, and good morning, good afternoon, good evening to everyone attending. I will begin my presentation by sort of giving you what is the final message. So I'll begin at the end. And the final message is that when you deal with the design of wideband systems, and we will clarify later in the presentation what a wideband system is, since the term is fairly used, is used in a fairly broad way. When you deal with the design of systems like this, there are multiple technologies that come into play. and that require trade-offs, and these trade-offs are fairly complex. And so it is important to be aware of the different compromises that need to be made, even though the technologies are fairly different. So let's begin with what applications are actually demanding for systems of this sort, and that will probably clarify what's the meaning of a wideband system. So in recent years, there has been an emergence of multiple applications that are really changing changing our field quite a bit. And so we see, of course, the emergence of demand for very high communication in data centers, in high-speed networks. Automotive is another area that is really experiencing quite a revolution, especially with the emergence of self-driving vehicles, and of course, Internet of Things and so on. All these different applications are demanding for higher and higher data throughput. And higher data throughput obviously depends on two things. It depends on dynamic range, and it depends on bandwidth. And obviously, the higher the dynamic range, the higher the bandwidth, the more data you can transfer on a given time. And if we concentrate on the bandwidth in particular, as we can see in this diagram over here, there is quite a bit of crowding of multiple communication systems in the frequency range that is of the order of 0 to 5 to 6 gigahertz. So everything is really happening over there. Of course, we're talking about also the ISM band and so on. If we look at the higher frequency, and here is a diagram that shows the attenuation of signals as a function of frequency. Well, if we look at the higher than 6 gigahertz or so, there is plenty of space, so to say. There is plenty of frequency ranges where one can allocate a wideband and therefore use these frequencies in order to transfer quite a bit of data. And applications that are driving the demand to go into higher and higher frequency and utilize higher and higher bandwidth include, for example, communication infrastructure. Everyone is talking about the 5G, and deployments are beginning to happen, but there is already talk about 6G or future networks. And of course, as I mentioned earlier, there is quite a bit of demand for higher data throughput for data center applications, communication backhaul, and new emerging applications such as immersive virtual reality, remote medicine, etc., broadband sensing, and so on. So when you look at operating at such high frequency and with increasing demand also for dynamic range, inevitably you're going to be faced with a problem of sort of a bottleneck resolution, in a sense that you will have different stages on your communication system where you will face limitations in terms of the bandwidth, in terms of the noise, and the linearity. And these bottlenecks will occur, as we will see in a minute, in different places, and not necessarily only in the electronics. So therefore, there is a constant series of trade-offs between what the applications are demanding in terms of higher throughput. And we have seen that there are several applications that are emerging and creating such demand. Then, of course, there are technology constraints which needs to be resolved. and technologies that need to be applied in order to overcome these limitations. But obviously, every technology has an implied cost, whether as a cost of development as well as a cost of, obviously, of the materials involved, the cost of using the technology. So there is a constant struggle and a constant trade-offs between the demands of the application, the actual technologies constraints, and the technologies that we want to make available to resolve that, and obviously business constraints, which allow us to use certain technologies versus others. So if we look at the entire stack of abstraction, going from process technology and devices, circuits, and then up to architectures and functions, and then putting them together to create systems, and ultimately all the application layer and the software that is needed to operate a system like this, there are several trade-offs that are done at each level of abstraction, but also between the different levels. For example, we can certainly design circuits if we have the right process, process technology, and at the same time, the type of performance that the devices can allow will inevitably condition the type of circuits that can be designed, which in turn determines what architectures are more applicable, and so on and so forth. And sometimes the trade-offs that are introduced when we do such designs can also be resolved by means of algorithms. For example, by using calibration, we can break inevitable trade-offs between for example, mismatch between passive devices and the frequency of operation of the circuits. Using algorithms, we can also eliminate imperfections that allow the use of interleaved architectures, for example, in theta converters, and so on and so forth. Algorithms also allow to improve the linearity of systems where the intrinsic linearity provided by the electronics is insufficient. There are also other technologies that come into play, such as, for example, packaging, which is becoming one of the large bottlenecks in terms of frequency operation, especially when you need to communicate data between the mixed signal front end and the digital processing, or even between the millimeter wave front end and the lower frequency RF section of a system. And there are also other trade-offs involved regarding the manufacturability of systems like this, as we will see in an example in a minute. So therefore, it's important to master each and every one of these technologies, but it's also very crucial to be able to understand the trade-offs that are implied when these technologies condition one another. And it's very hard, therefore, to do a consistent top-down design. Oftentimes, it's really a combination of top-down design and bottom-up in order to resolve all these constraints and bottlenecks. And as I said, it's also very critically important to keep in mind the cost of these trade-offs, because obviously higher performing, let's say, packages will cost more, or a faster process technology will cost more, and so on and so forth. So let's consider the example of wireless infrastructure connectivity. In other words, base station for cell phone communication. Now, as I mentioned earlier, there is a constant advance in the generations of communication systems, and we are today in the early days of 5G deployment. 5G is generally distinguished in sub-6 gigahertz 5G, meaning the bandwidth allocated for communication reside below 6 gigahertz. And here is an example of some of the most popular bandwidth allocations across different countries. And the next deployment will involve what is normally referred to as millimeter wave 5G, where the bandwidths are allocated in the range of 24 to 30 gigahertz, and additional bandwidths are already being planned in the 49, 50 gigahertz. And then there is discussion for so-called 6G to go at 60 and even beyond 100 gigahertz. As I mentioned earlier, this allows to utilize wider bandwidths, which obviously imply higher data throughput, but they obviously come with significant technical challenges. So here is a diagram kind of summarizing what 5G is, and it's not only cell phones, but it's really a confluence of multiple other communication technologies, notably video streaming demands for much higher bandwidth than most cell phones will actually implement. There is obviously also other critical requirements. It's not only about bandwidth and data throughput, it's about also lower and lower latency of communication, especially when the communication needs to be much faster, not in terms of data throughput, but really the speed at which data is communicated. And these include mission critical applications, self-driving cars that obviously need to be responding very quickly, and so on. One important technology that has been introduced as we transition from 4G to 5G is the use of beamformers. So in 4G, in most cases, the communication between the base station and the UEs, which are the devices that are in communication with the base station, is generally done via either broadcasting or analog beamforming. And with analog, and in the case of analog beamforming, typically the beam is one and fairly broad oftentimes, and multiple users link to the base station using that. In 5G, with the introduction of more digital beamformers and phased arrays, then it is possible to create dedicated links between the beamformer, the antenna array, and each of the devices that need to connect to the base station. This has many advantages, one of which is, of course, the one to use space multiplexing and therefore deal better with the interferer. So an interferer that obviously is located outside the beam will create less disturbance to the link between a user device and the base station and so forth. And it's important also to realize all these beams simultaneously. So we can actually see this really in the different generations of base stations, where many years ago, in older generations, you had a single antenna that would broadcast, and then all the electronics would really sit at the base of the base station. But as things have evolved, the number of antennas has increased. And again, as I mentioned, today really people are building phased arrays of antennas, where much of the millimeter wave RF and mixed signal electronics actually resides together with the antennas. And in fact, an entire transceiver, an entire mixed signal transceiver is typically connected to a small subarray of the entire beamforming antenna, while much of the digital unit actually sits separately and often at the base of the base station. So these are examples of early phased arrays for sub 6G. So one thing that you will probably notice is that all these are all antennas. So you can see here in this example an 8x8 array made of 64 antennas. And in order to create a beam without so-called grating lobes, which are undesired, the space limitation is that the distance between one antenna and the other needs to be equal to lambda over 2 or less. And lambda over 2 is where lambda is the wavelength corresponding to the frequency of operation. So for 5 gigahertz or so, lambda over 2 is of the order of 3 centimeters, which means that these antennas need to be 3 centimeters to one another or less. And if we're really talking about now millimeter wave, so in the order of about 30 gigahertz and 40 gigahertz, then we are really talking about 10 times less in terms of this distance. So what happens now is that all the electronics needs to sit right behind these antennas. And if we want to have an entire transmit and receive chain for each individual antenna in order to create a so-called digital beamformer, which will allow us to have multiple beams and control them with high accuracy and create a link with different users, you can see that we have a space restriction. The space restriction implies multiple challenges. One challenge, there's an echo perhaps. One challenge is that the electronics, especially the PA, consume quite a bit of power, and the power delivers heat, and heat needs to be removed. Otherwise, we will have thermal problems of all sorts that could lead to degradation in performance and ultimately to failures. So as you can see, there is a manufacturability problem that immediately arises from a space restriction. And so there are different technologies that are employed to extract the heat, to manage the heat. But more importantly, this drives a demand on the power consumption of the electronics, not just because of the energy that is required to operate the system, but also because obviously the electronics will not perform if the heat is excessive. So as you can see, there is an immediate trade-off here between different technologies, not just the electronics per se. So let's look at what a high-level diagram of the electronics that sits behind the antennas. So we have here the antennas elements. Each of them has a PA and an LNA and a filter that separates the transmit from the receive, which is called the duplexer, and we'll look at that in a minute. These arrays of TR modules feeds our initial beamformer, which is done in an analog way using analog phase shifters. So essentially, the entire array is often partitioned in subarrays, each of them being an analog beamformer. And the analog beamformer combines some of the antennas and then communicates with the millimeter wave analog up and down converters. So the mixers and the filters that allow to go from an intermediate frequency over here to a millimeter wave frequency over here. And then ultimately, when you get to the intermediate frequency with the data converters, the D to A for transmit and the A to D for receive, then you can bring all the channels into the digital domain where they can be further digitally filtered, up converted, and down converted digitally. And ultimately, this array of digital analog and digital receive and transmit channels, then they get combined by using a digital beamformer. In fact, an entire set of digital beamformers, one for each beam, for each link that you realize and control. And so a system like this obviously has multiple bottlenecks, so to say. In fact, at every one of these transition points between the different stages of transmit and receive, up conversion and down conversion, you're going to have to deal with different type of limitations and restrictions in bandwidth, in noise, and in linearity. And obviously in the digital domain, the ability to transfer this data at the proper speed. So let's look at the analog and the millimeter wave section of one of these multiple signal chains. So we have the transmit path up here and the receive path down here. The antenna is being used both by the transmit and the receive. And the transmit, of course, has the PA and the the millimeter wave up converter and the DAC. And then in the receive, we have the LNA, the down conversion mixer, and the ADC. And then there are filters in between. Now, when we look at a system like this, one of the major contributors to power is the PA. And in addition to that, the PA is typically not very efficient from a power point of view. And efficiencies are of the order of 10% to 20%, depending on the technology used for the PA and depending on the ability to do digital pre-distortion. But the big issue is, of course, power consumption, and the big issue is that the power that is not effectively transmitted, it's basically dissipated, which means it creates heat. And that's one of the problems I was alluding to earlier when we were looking at the antenna array. Other blocks that tend to have a non-negligible amount of the power consumption include the data converters and especially the baseband processing that is generally connected to the data converters. This one well before we actually end up to the beamformer. So the other problem that goes beyond all of this is the filters. Because much of the electronics, especially this part of the electronics, the RF transceiver, can actually benefit to some extent of Moore's law. We're going to have a look at that in a few slides. But many of the filters employed over here, including the duplexers, but also some of the other millimeter wave filters, unfortunately, do not benefit of Moore's law. They don't scale, they are large, their size depend on the frequency, and their cost also depend on their size. So these are challenges, and what people have been trying to do most recently is to change the electronics, the architectures, especially in the transceivers, in order to simplify the discrete filters, in order to make them simpler, lower order, essentially, smaller, compromise, of course, of the performance, but then compensate for the loss in performance of the filters by doing other things in the transceiver. And this is just to give you a sense that this is a duplexer from an old 3G base station. And as you can see, yours truly here holding one such duplexer. This certainly is not scaling well with Moore's law. Obviously, this is an older filter, and newer filters have already been simplified, but that really gets you a sense of the order of magnitude we're talking about here. And this is the power amplifier. As you can see, the power amplifier dissipates a lot of heat. This behind here, the back of this board, that's the heat sink to be able to dissipate the heat. So yeah, I mean, when we really talk about the integration of transistors, we are on a different mindset as to what happens in front of a system like this. Now, that sets the stage for what technologies can we use to solve some of these problems. So let's start from device technology. As I mentioned earlier, Moore's law helps quite a bit for part of the electronics. Now, one thing, however, is that Moore's law has been much topic of debate in late years, and in fact, there is a joke that says that the Moore's law essentially says that the number of people that say the Moore's law is dead doubles every year. But seriously, the improvements have been different in the last, let's say, 5-10 years than they have been in the early years of scaling. Gate delay, it's continuing to decrease, though not at the same pace as in the past. So in other words, the digital gates are getting slightly faster at each generation. But the more important thing is that the switching energy, it's actually continuing to scale. So, so digital power consumption does actually benefit of scaling. And so does area. So shrinking sizes are indeed continuing, although again, not at the same rate as in the past. And even we should mention, and even today when people talk about 7 nanometers or 5 nanometers, it doesn't really correspond to actual sizes. It's really more of a marketing term, because 7 and 5 nanometers is more like 18 nanometers in actuality. But anyway, here I have a plot that I created to show a couple of trends. On the x-axis, we have time, and that implies technology adoption, and specifically this represents the 65 nanometers, 28 nanometers, 16 nanometers, and then a projection on 7 and 5 nanometers. As process has shrunk, the gate power has continued to go down, which is what I was mentioning earlier. Gates are actually becoming more and more power efficient in a very substantial way. Gate speed has improved, though not a whole lot. If we look at other parameters that are more meaningful for analog, we can consider, for example, the transition frequency, FT. And the transition frequency has improved quite a bit from 65 to 28 nanometer, where it basically doubled. And it has changed a little bit when there has been a transition from 28 nanometer planar to 16 nanometer FinFET. It's slightly decreased, maybe improved as the process has matured, and it's slightly increasing in next lithographies. But not a whole lot. The plot that I'd like you to pay attention to is this blue curve. The blue curve over here is the requirement on instantaneous bandwidth. So the bandwidth required in typical base station electronics. So we're looking at 75 megahertz at this time, which have then grown to 100, 200 megahertz, 400 megahertz, and today we are really of the order of 800 megahertz. Notice here the logarithmic scales. The point here is that the demand for bandwidth have gone up much faster than the ability of the process to support the bandwidth, which is, for example, represented by FT, or in a way you can look at also gate speed. So in other words, if during this time we could build switch capacitor systems such as A2Ds or other data converters by porting an architecture from one process to the next and still able to cope with the demand for bandwidth, at some point, this has not become possible anymore. The demand for bandwidth has gone up so fast that it's inevitable that an architectural change has been required. And this has been actually enabled by new architectures, such as finally the ability to make time interleaved converters work. In time interleaved converters have begun to become real and feasible thanks to digital calibration. And digital calibration is what is enabled by Moore's law. It's what is enabled by the availability of smaller and smaller digital gates, which indeed consume less and less energy in terms of digital functions. So as you can see, Moore's law comes here in a sort of indirect way and helps analog by digital assistance, not in a direct way by improving the actual device performance. Unfortunately, the FT doesn't say the whole story. And that is because the strays that are associated with the interconnects have actually become the real challenge as we scale into finer lithography. And you can see over here, for example, the resistivity for the interconnects have increased dramatically, especially in finer lithography, newer generations. Capacitance has also become higher, but not at the same pace. So really much of the issue comes when we need to have long interconnects, when we need to use plenty of vias, and that's problematic. There are ways to get around it and mitigate it, but really not to solve it. So that's a big constraint that comes in the form of layout. Another problem is due to electromigration. At higher temperature, obviously, we experience electromigration, and especially where there is high current density. So obviously, to relieve the bottleneck due to the high current density, we need to make conductors wider and reduce the density. But that's exactly the wrong thing to do when you want to go faster, because obviously now you're increasing the strays, particularly the capacitive strays. And then there is another problem that has to do with temperature and current density, high current density, and that's device aging. So what happens is, because of effects like Hall carrier injection and NBTI degradation for some devices and PBTI degradation for other devices like NMOS, the threshold voltage of the devices begins to shift over time, and the shift is accelerated by high temperature and high current density. So what happens is that the devices that begin operating with less and less current capability. So you can see a device which had this ID characteristic over time, and at a high temperature will shift, and the drain current will begin to go down over time. And so in this example, VCO will begin shift its oscillation, its frequency of oscillation, and so on. And these are things that needs to be simulated and need to be taken into account. And last but not least, as I mentioned earlier, cost. The cost of implementing and the cost of designing systems in finer and finer lithography has been increasing exponentially. And that is due to a number of reasons, some of which have to do with the intrinsic complexity of designing in finer lithography, and another one due to the fact that obviously when we go to more integrated system, we add a lot more functionality, and obviously just because of that, the complexity increases and the cost increases. And one of the components that is increasing the most is actually verification, much more than actual transistor level design and physical design. So the layout essentially is it's another important component of the cost. So let's look at some converter architectures and how these have evolved. This plot shows the converters published at ISSCC and at the VLSI conference in the last 20-something years. The plot dates back to a couple of years ago, but it's sufficient to make the point. Now, what we call the high-speed converters, which are the type of converters used in wireless infrastructure, so the example that we've been looking at, they reside in this region of the input frequency versus signal to noise and distortion ratio space. And in this plot, going higher means, of course, going higher frequency, going higher signal and dynamic signal to noise and distortion ratio. If we zoom into that region that I highlighted, we can see that there are multiple architectures of converters. So we have continuous time delta sigmas over here for higher dynamic range and slightly lower input frequency. And on the opposite side, we have time interleaved discrete time for switch capacitor converters such as pipelines, or sometimes switch capacitor successive approximation converters. Here is an example of a recently published 8 times interleaved pipeline A to D. Each channel is a pipeline A to D, and there is 8 of them. In fact, 7 of them are interleaved, and an 8th one is used for scrambling. And here is a summary of the performance. Is nominally a 12-bit 10 gigasample per second A to D. And as you can see, the noise and distortion are actually sustained over a very wide range of input frequencies. And this one is a 28 nanometer converter, and it consumes short of 3 watts in order to realize this performance. Everything is calibrated here at the sub-block level, so at the MDAC level. And then, of course, the mismatches between the A to Ds are also calibrated, and ultimately, any residual distortion is eliminated through the use of random shuffling between the order of the converters. A second generation is shown here. This is a paper that was published only a few months ago at ISSCC. This is a 16 nanometer, 12 bits. The sample rate is nearly double. And despite that, the power consumption at this sample rate is nearly half to perhaps even less than half, 1.3 watts. In this A to D, in addition to obviously the benefit of 16 nanometer, there are architectural changes that have been made. Everything has been calibrated much more heavily than in the prior one. And there is use of different architectures for the amplifiers, which are much faster. They are open loop architectures, which allow to go much faster. They introduce more distortion, but then the distortion is digitally calibrated. And then there is a difference in the way the sampling is being done, which I'm not going to get into here. A different architecture that is also emerging is the one of continuous time pipeline A2Ds, which is essentially similar to a discrete time pipeline A2D, except that each stage is implemented by using continuous time circuitry. And this tries to marry the advantages of classic pipeline A2Ds with the advantages of continuous time delta sigmas. And obvious advantage of continuous time delta sigma is the ability to drive its input, which is a benign passive load, nominally a resistive load. In this prototype, we were able to demonstrate an input bandwidth of the order of 1.2 gigahertz with very high linearity and very low noise. However, in order to improve that, one improvement that was made was in the following generation was to replace the back end, the stages after the first stage, by using a VCO ADC. A VCO ADC, which is here shown, is a rather complex circuit, but one way to understand it is essentially what you have is that you have a ring oscillator, which is essentially a digital circuit, and the frequency of this ring oscillator is controlled by the analog input. So for higher input voltage, you get a higher output frequency. Now, if you count on a given time how many oscillations do you have, effectively you can determine the frequency. And so you have essentially done an A to D conversion from the input voltage to the frequency to the number of zero crossing in that set amount of time. So that allows you to do the conversion. Why doing that? Well, because an architecture like this benefits of Moore's law. The ring oscillator essentially is a cascade of digital gates, and so it can be made very small. And all the calibration that is required in order to make it linear is also fully digital. So this can actually be made very small, very power efficient, and benefit of Moore's law. So as I said, an architecture that was recently published just a few months ago in 16 nanometer is a continuous time pipeline A2D, where the front stage is a continuous time structure, and the second stage is a VCO ADC. And by doing so, we were able to demonstrate a bandwidth of the order of 800 megahertz with a power consumption of only short of 300 milliwatts in 16 nanometer, and noise and linearity that is very much adequate for wireless infrastructure application. As you can see here, we are really looking at, where is it? Here, 153 dBFS. Sorry, this is the figure on merit. Somewhere over here, it should be. Anyway, the noise spectral density is of the order of the nearly 150 dBFS over hertz, and very high linearity. Now, what do we do then? Then we have all these converters and mixers, etc., and we need to build integrated systems. And sometimes the integrated systems are going to be composed of the RF front end, the transceiver, and the digital backend that does much of the DSP. So we need, one way to do this is through systems on a chip, in some cases, systems in a package. So let's look at packages. A classic package that is used in systems like this is a BGA, a ball grid array. And these are examples of ball grid arrays and flip chip ball grid arrays. As I mentioned, the power consumption, or rather heat dissipation, is one of the issues. So some of these packages actually can benefit of a heat sink that is placed on top. And for millimeter wave front ends and modules, in order to accomplish high frequency performance, there are specialized packages that tend to be smaller and cannot allocate large dies. These are some of the examples. And in general, there is a trade-off in the different packages between the RF performance and the size of the die that can be used and the number of pins. So we have BGAs here that allow large dies and high number of pins. On the opposite end, we have a wafer level chip scale packages which allow a higher frequency performance, but they only can accommodate smaller size. So here is a different trade-off that needs to be done, where you need to decide which sections of your system need to put in each package. However, in order to be able to integrate in a package larger system composed of multiple dies, the 3D packaging is becoming an emerging approach. So we're talking about here heterogeneous integration, where multiple dies are stacked on top of each other, and the different dies can actually be contacted together in order to exchange signals with very little strays. And here is an example of a system on a package using a silicon interposer, where different parts of the system, the digital and the analog and the RF, can actually reside together on a common interposer, a silicon interposer, and the signals can actually be exchanged from one another directly without going to the board and using sometimes through silicon vias connectors. And ultimately, this subsystem is connected to the board via a ball grid array. Integration for the purpose of higher density is also driving new developments in device technology, where FinFETs are going to be soon replaced by gate-all-around devices, where the gate, where the fin essentially wraps around the entire channel. And there is also effort to stack multiple devices one on top of each other, and so create very short connections from one device to the other one that is connected, and increase density. So that helps by reducing the parasitics. It also creates problems in terms of heat management, because obviously extracting the heat from these stacks is very difficult, and obviously costs are high. One more thing that I want to talk about before I close my talk is the use of algorithms in order to improve the performance of complete systems. I alluded to that at the beginning, and I'll show you an example of a digital post-distortion approach that allows to improve the linearity of an entire chain in a system like those that we discussed. So here we have an example of one such system from where the mixer provides an input to an input driver, and so a buffer for an ADC. Obviously, there is an anti-aliasing filter, and finally, the ADC. In cases like this, the ADC often performs better than the chain in front of the ADC. In other words, the ADC tends to have generally higher linearity and noise than the input buffer and the mixer. When we put all the blocks together, the entire chain will have a combined nonlinearity, which I sketched here as an example. And some of this nonlinearity stems from the input driver in this example, and especially arises when we connect the input driver to the filter to the ADC. So one thing that we can do is that we can try to make a model, a mathematical model, a digital model of this nonlinearity. Let's call it H of C, with some parameters of this model C. The model can reside with the A to D because ultimately will be a digital representation of this nonlinearity. Typically, on the same chip, we will have a microcontroller that is used to calibrate the ADC. And so we assume that the ADC here is calibrated already. So what we can do is that we can also have a DAC, and typically DACs can be made fairly linear and at very high frequency. And with this DAC, we inject an input test signal in front of the buffer. And when we do that, the system is not operating. There is no signal going through from the mixer. So this is a foreground calibration. And we use the microcontroller to create the test signals. The test signals are injected. They go through the input buffer and ultimately reach the ADC and create a digital output. We know what we created, what signal we injected, and we can see what signal has been returned at the output of the ADC. And therefore, we can use this information to identify the coefficients of the model. We use this information in order to identify the nonlinearity. And we do that in situ, meaning on the board where all the components are operating. When we have this information, we actually have realized this model. We can stop the DAC. The DAC doesn't inject anymore. We have the information in the form of the model, in form of the parameter values for the model. And therefore, we can now use the model to invert the nonlinearity from this point to this point, and therefore linearize the output by inversion using the model. So that's what is classically called digital post distortion. These are some examples that we have measured in the lab. The purple curves show the second harmonic distortion over different frequencies. This is using the ADC, the 12-bit 10 gigahertz sample per second ADC, now clocked at 6 gigahertz. So this is the blue curve is the second order harmonic distortion before calibration. Here is the third order harmonic distortion before calibration. After calibration, as you can see, both the second as well as the third have improved across all frequencies by, in some cases, even by 10 dBs. And so that's because of the linearization. And the linearization ceases to become effective at nearly 80% of the some of the Nyquist frequency, and that's because we use essentially a digital filter model. So obviously that's limited as to which frequency can actually work. This plot shows the SNR is not changed by this calibration, so there is no impact to noise. And the spurious free dynamic range also has benefited of the linearization across all frequencies. Here is a practical example. We apply a Wi-Fi signal. That's the blue signal, and here it's overlapped, so you cannot see clearly. And there is distortion. You can see here the second harmonic distortion, the third harmonic distortion, and higher orders. And then after calibration, we get the red curve where the distortion has been completely eliminated. So in conclusion, as I mentioned before, there are multiple technologies and multiple challenges that they all come into play and they need to be traded off from one another. Challenges include the heat removal, the device reliability, aging, and of course the cost and the challenges associated with process technology, packaging, data interfaces is not something that we talked about a whole lot, but that's another important challenge. And obviously, we need to balance performance, cost, bandwidth, etc. And it's important that we understand all these trade-offs because, again, not a single one will actually determine the ultimate performance, but it's a matter of really finding the right trade-offs and finding the right cost points for each of them. And that concludes my talk.
Okay, thank you very much. It's very interesting talk. In fact, I learned a lot. So we have still time for some questions.
Yeah.
So I will see if someone did one. Well, I think I will start. So you mentioned that one of the important parts of the system is the power amplifiers.
Yep.
What is the average power that's necessary to transmit the signals in a bin array for the 5G communication?
Yeah, obviously it depends from the size. So it depends on the distance at which you need to transmit, right? And it depends also on the size of the array. The more elements you have in the array, the more combined power you can realize at a given distance. Typical numbers for millimeter wave applications range of the order of 15 to 20 dBm of power that needs to be transmitted. So this translates in the order of watts for the power consumption of the PA, and typical technologies that are used for this order of magnitude range from ideally gallium nitride processes that give you the best power, but they have their own challenges, and they are fairly efficient. On the other hand, for much lower power, you can actually use either gallium arsenide or CMOS in some cases for the lowest power. Obviously, there is a cost versus performance trade-off, but yeah, effectively, we're really talking about watts, a few watts, quite a bit. In some cases, even close to even tens of watts, and transmitted power of the order between 10 to 20 dBm.
Okay, thank you. So I got some questions from the audience. So Professor Hugo Fernandes from the University of Minas Gerais, on the gigahertz ADC chips, is the clock generator included on the chip? Does the clock jitter has a huge impact on the ADC as an SNDR specs?
Yeah, so yes, the clock jitter and the power required to generate a low phase noise are very, very important. Are very important to this, because obviously, so for an ADC, the jitter essentially limits the noise, and that depends directly on the frequency of the signal digitized by the A to D. So obviously, the higher the input frequency, the tighter becomes the requirement on the clock jitter. And the clock jitter is realized oftentimes with a PLL, and the power consumed by the VCO obviously increases with the requirement on the jitter, the phase noise. There was actually recently a paper published by Behzad Razavi at ISCAS, where it showed that while in principle to increase the frequency of operation of an A to D, you go linearly in power for linear increasing frequency, the power consumed to realize the phase noise goes up quadratically. So that's actually a concern. And yes, typically in systems like this, what you do is that you try to create the clock for the converters using a clock synthesizer. Ideally, you will want to have a VCXO, because obviously it gives you a very low phase noise, but it's relatively narrow in frequency or fixed in some cases in frequency. People are trying to do this with integrated PLLs, and using obviously LC tank oscillators for the VCOs. The power consumption associated with the clock generation and the clock distribution, it's certainly one big component to the power budget. It's comparable to the power consumed by the ADCs. And yes, I acknowledge the concerning trend that was highlighted by Razavi's paper at ADCs just a few days ago.
Oh, okay, thank you. So we have another question from the audience, from Fabio Kellum. He's from Eldorado Research Institute. So he asked, do you think the demand for high bandwidth will make ADC technology to get special process technology outside silicon? Will this be the same as other RF process?
So, well, let's see if I well understood the question. Essentially, the demand for wideband systems and wideband converters is driven by a number of applications. And obviously, the most direct demand comes from applications that require wider band. These include at the very end, really things like military applications, such as electronic warfare, where people really want to digitize and synthesize a huge amount of bandwidth. The wider, the better. And other applications, of course, as I mentioned here, include different types of communications, such as those required for immersive virtual reality. We're really talking about there for bandwidths of the order of, let's say, 2 gigahertz, sometimes more. And then, of course, multi-standard millimeter wave communication, like the one I discussed, where the instantaneous band is of the order of 1.2 to 1.6 gigahertz. Not sure if that was the question, but...
Okay, thank you. So I would like to ask something else, still on the power. So on the average, what is the maximum distance allowed between the repetition of the stations, power stations? The antenna.
Sorry, say again. What is?
On the average, what is the maximum distance between the repetition of the stations for the communication in large cities?
The distance between the base station and the used device. Okay, so yeah, so this one depends on many things, but for millimeter wave 5G, we're really talking about, let's say, a floor, an office floor. So we're not really talking about things like kilometers, such as the case for larger base stations, because obviously there is an intrinsic issue with the attenuation at high frequency, how far you can actually transmit a given power. And so, as I mentioned before, it all comes down to the size of the array. It comes down to the ability to transmit that power and meet the requirements on EIRP, which is essentially how much power you can actually deliver at a given distance to the user. We're really talking about, several hundreds of meters. We're not talking about kilometers here.
Okay. So if I use 212, the main part will be distributed by fiber optics, and then locally you need some base stations.
That's correct. That's correct. So we're talking about what people refer to sometimes like small cells, pico cells, etc. So for larger, for smaller areas, and then you have many of them covering an extensive area, and then everything that then gets combined, of course, at wired level. And then you use instead the classic macro base stations instead to cover large areas. But this is driven essentially by things like urbanization, like in the centers of cities where you have many users on a small geographic area, and these users are obviously all competing for bandwidth and access to the base station.
Okay, thank you. In fact, Fabio Kelm, he gave a feedback. In fact, it was a more related to fabrication process, like silicon versus gallium arsenide versus gallium nitride, but it was still good information. Thank you. Is there any more that want to make any question to Dr. Gabriele? So some people thank you for the nice presentation. So the talk, it was very interesting. So and we were very happy that you accepted this talk. Although we are virtually, but we still learn about this. And so thank you very much, and see you maybe next year in Brazil.
Thank you so much. I really appreciated your invitation. It was a pleasure.
Okay, thank you. Bye.
Bye-bye.